Hello, thank you for the introduction. My name is Italo da Costa. I am a postdoctoral researcher at EPFL. And today I am going to present on behalf of my co-authors our work entitled SmarPer, Context-Aware and Automatic Runtime Permissions for Mobile Devices. As we all know, smartphones store an increasing amount of sensitive information about users, and permission systems are the main mechanism that users have to control how apps access this sensitive information. As of today, current mobile platforms such as Android and iOS use a permission system that behaves more or less the same. After an app is installed, the first time the app requests for a sensitive resource, the user is prompted and asks if this request should be allowed or denied. The decision is there stored, and it can be modified later on by the user by going through some menus. So I am sure all of you are familiar with this. This is pretty straightforward, and it's an improvement over previous permission models, but there are several limitations that affect how effective this is in practice. So one of the limitations that we have with current permission system is that these decisions are static. That is, they don't change according to different contexts of the user. And as we know, research has shown that user privacy decisions are context dependent. A user may be willing to share, for example, the location with an app if the user is actively using the app, but may not be willing to share the location if it's not using the app. This could be solved, for example, if we prompt the user every time there is a request for a sensitive resource, but we know this is not practical because we have too many apps. Apps have several permissions, and more importantly, apps are requesting with a high frequency this access to resources. So we can have tens to hundreds to thousands of requests per day. And this obviously will overwhelm the user or get the user habituated to the permission prompts, making them ineffective. Another problem is that users can only allow, that means that provide full access to a sensitive resource and have no privacy, or can only deny, and in some cases have no utility at all by denying access to a resource to an app. As a result, what we have today is, in reality, as somebody commented before me, users will tend just to allow all these permissions all the time and overshare sensitive information with apps. So in practice, these permission systems are not working as intended. So the goal of our work is first determine if we can automate permission decisions so we can prompt users and runtime without overwhelming them. And for this, we can use then machine learning techniques and contextual features to see if we can really learn the unique privacy preferences of each user. Second, we want to provide users with additional decision levels, not only allow or deny, but intermediate levels where you can share partial information in order to gain some utility and obtain a better balance between privacy and utility. So we envision these goals as a more advanced permission system that we name SmarPer for Smart Permissions. And here we can see the general design of the system. So it works as follows. We intercept app permission request, capture the context associated with that request, and we convert this into a feature vector that will be the input to a machine learning model that will output a prediction that can be allowed, deny, or obfuscate. Then we have a function C that will determine if this decision should be automated, that we take the prediction given by the machine learning model, or if we should prompt the user instead to give the responsibility to the user to make the decision. Then for example, if the decision is obfuscate, we contact our obfuscation module, and at the end, we provide a response to the app. All the decisions are then stored in a database that can be later on accessed by the user and modified to correct any errors. And periodically, the new decisions are used to update the model and then adapt to the behavior of the user. As we know, users will tend to change their privacy behavior over time. Something important is that SmarPer is not designed to make better decisions. Instead, SmarPer is designed to mimic user behavior when making decisions. That, for example, if the user is allowing all the time, then SmarPer will learn to do that. So for this, obviously, to implement this system in practice, we need data to do our machine learning analysis. At the moment we started this work, there was not a data set with real-time, runtime permission decisions. So therefore, we decided to collect our own data. For this, we designed an experiment, and we implemented a prototype of SmarPer to collect permission decisions at runtime. And in addition, we implemented data obfuscation techniques for 4 data types: location, contacts, storage, and camera. We then ran a data collection campaign with users in a realistic scenario and used the data collected to perform on data analysis, machine learning modeling, and evaluation. Here we have the results of our data collection campaign. We collected data from 41 users that participated in our study for a minimum of 10 days. Some users used their own phones, while to others we provided phones for the study. In addition, we didn't prompt the user all the time. We instead introduced some heuristic to regulate the number of prompts we were showing to the user to avoid overwhelming them. So on average, users were prompted around 17 times a day. We collected decision data from 23 popular apps. And why popular apps only? First, to guarantee that the users interact with the app during the study, and henceforth produce decision prompts for permissions. And second, to reduce the chance of data sparsity, because if we collect permissions requests from any app, then we will have little data from too many apps, so we will have to deal with sparsity. In total, we collected 8,521 permission decisions, which is, as far as we know, the largest data set of this type. And we did it, again, for 3 permissions or data types: location, contact, and storage, again, to reduce the chance of having data sparsity. For each permission decision, then we collected 32 contextual features using the standard Android API. So here we have some results of the data collection campaign. We show the histogram of the number of decisions collected per user. And we can see that for some users we have relatively little data, around 75 decisions, and for other users we have close to 550. We can see also the distribution of allow, obfuscate, and deny, and they are more or less balanced. And we can see that, well, with some bias towards allow. We can also see that users have different behaviors already from this histogram. We can see, for example, that some users were denying, at least 2 users were denying most of the time, while other users were trying to allow most of the time. And we can see all other kind of behavior or distribution of decisions per user. An important takeaway from this is that we were quite pleased that most users were positive about the use of obfuscation. We found very few issues with compatibility with apps. An exit survey that we did with the users, 73% of them reported that they found obfuscation useful and that they will be interested in seeing obfuscation techniques for other data types. So in this plot, we show how permission decisions change over time. Here we see for all the users that use WhatsApp in our study, their decisions about letting WhatsApp access the storage, external storage. Each block is a decision, And we have the decisions, a set of decisions at the beginning of the study, in the middle of the study, and at the end of the study. And what we can see here is that except the first user at the top, all the other users did at least 2 types of decisions. And in some cases, some users did 3 types of decisions for the same app and permission request. So again, this is a proof that indeed current permission system cannot capture this behavior. They fail to match this behavior, and therefore is a trade-off for the users in a negative way. So, having the data, then we proceed to do the machine learning analysis. Because we have limited data for some users, around 75 decisions, then we decided to focus first in the simplest approach of machine learning model that we could use. In this case, a linear regression model. We model this as a linear problem, and we use Bayesian linear regression, which is recommended for these small data sets. In addition, we evaluated more advanced models, being aware of the risk of possibly overfitting, and we consider 2 approaches. Training a single model with all the data from all the users, that is the one-size-fits-all approach, or training a per user model. For comparing all these models, then we implemented a machine learning framework to have a fair comparison. We also consider 2 baselines. The first baseline we call static policies, and it's an approximation to what current permission system, how current permission systems work. And the second baseline, we call it 0RT, which is a simple model that will output as a prediction the most frequent level observed at time t. This is a model that do not take context into account, but take into account previous decisions. To compare the different models, then we use a standard error measure presented here. Basically, what we do here is, first, we compute the average error of the decision for a single user using a loss function that I will introduce next. And then we compute the average across all the users. And we do this to penalize models that do not generalize well across users. So we consider 2 loss functions that then produce 2 types of error. We consider the 0-1 loss, which is quite popular, that allows us to estimate the incorrect classification rate, ICR. But the problem with this metric is that, or this error, is that it ignores the ordering between the type of decisions. For example, if I predict allow instead of deny, it will be the same that predicting allow instead of obfuscate. And we can see that this is not necessarily the same. So for this, then we consider another type of error that we call the mean absolute error, MAE, where we encode allow, obfuscate, deny decisions as -1, 0, and 1. And in this case, if we predict allow instead of deny, we will have an error of 2. And if we predict allow instead of obfuscate, we will have an error type of 1. So then we can take into account these different types of errors. So here we can see the results of our performance evaluation. So we have in the y-axis the mean absolute error, MAE, and in the x-axis the percentage of training data of decisions used to train the model. So we start with 10% until 100% of the training data, and the idea is here to see how, with more training data, which is obvious, we increase performance. And here, by increasing performance, I mean lower the error, or lower error. So the plot that we are seeing here is for our baselines that in general do not take context into account. We see that for the static policy, we have just a straight line because it does not take future decisions into account. It's a static policy. And we have the 0RT, which improves slightly with more data, but does not after 60%. The shadow shows the 25th and 75th percentile, so you see that there is some variability there going on. Now, we can see the performance of models using the one-size-fits-all approach that is training with data from all the users. And we can see that their performance is worse than our baselines. And the reason for this is that the behavior of the user is so different that, at least with the model we use, was difficult to capture accurately with a single model, predict for all the users. Now, on the contrary, if we train a model per user, we have much more better results. Now we see that taking into account the context and a model per user, then our performance is much better. And for all the models that we consider in this way, the performance was more or less the same, but we reported the result for Bayesian linear regression because it's the simplest model we consider and the easiest to interpret. And we achieved an error of 0.22 that is approximately 80% CCR, or correct classification rate. This is great because we show that then, even with a simple model, we can predict quite accurately decisions of the users, even with a small amount of data. And we can see from the trend of the plot that even if we have more training data, we could even achieve more accuracy. Now, we have shown that we can learn to predict user decisions, even with limited amount of data. Now, what is needed to automate decisions? So here we face several challenges. First, we need to determine how much time and training data we need to have enough accuracy to start automating or have accurate predictions. Again, this is user dependent. So it depends how willing is the user to provide us with decisions. And second, how easy or difficult is the user to predict. For this, then a longer term study is needed and with different type of users. So to reduce the amount of time needed for this, we can use clustering techniques. So we can, for example, identify type of users and then have pre-computed models so the user start with these models instead of training a model from scratch to accelerate the process. But again, we have only 41 users, so we couldn't really do clustering analysis here. So in addition to longer term study, we need then more users. A more important question is how to decide when to prompt the user or make a decision automatically based on the prediction of the model. Initially, we thought that we could use only confidence metrics such as the probability of a label to make such a decision. But in our analysis, we identified that there are other factors that need to be taken into account. For example, we cannot prompt the user all the time, so we have to take into account how many times we have prompted the user. We also cannot just automate all the time because we always need new data to keep the model updated and to keep the accuracy of the model. So henceforth, we need, again, more data to evaluate more advanced techniques to have not only better accuracy, but also better, consider better techniques to decide when to prompt the user. To summarize, we have collected a unique data set of decisions collected in real scenarios and for 3 decision types, allow, obfuscate, and deny, and this data set is available to the community. We have shown that it's possible to learn how, or to predict how users make decisions, and the context is critical for this. And we can do this with reasonable accuracy, even with limited amount of decision data. This is a great step towards automating decisions, but still, there are several challenges that we will face, we are facing in future work. Finally, we have successfully evaluated and tested the obfuscation technique with users, and we got really positive feedback. All our data and our code is available in the SmarPer website. Here's the URL. And with that, I will conclude and will take your questions. Thank you.
I have time for one question.
Yeah, thanks for the talk. I had one quick question about the second model that you mentioned where you created a model per user, the context-aware model that you mentioned. User habituation tends to be a big problem, right? When you're collecting data, you're prompting them a lot. How do you address the habituation problem when you have one model per user?
How address the problem of
like user habituation, like basically showing them too many prompts where you're kind of giving them decision fatigue. Just kind of like, do you have numbers around that, or just an explanation of how you would avoid that?
I'm sorry, I don't understand. Could you speak a little slower?
Oh, sorry, yeah. So for the second model that you had, where you were training one model per user.
One model per user, right?
Right. That sounds like it would require a lot of decisions from each user.
Yes, yes.
So that could potentially habituate the user or create a lot of annoyance. Is there is there a way to mitigate that?
Yes, yes. So yes. So during the study, what we did is we use some heuristic to regulate the number of prompts to the user. And when we couldn't prompt the user, then we use a static policy. Okay, what was the last decision for this particular request, or what will be the policy defined by the user. But this was for the study. In practice, what we'll expect is that initially the user will not start to collect data for all possible apps. You can start with a subset of apps, and then start collecting decision periodically, with certain frequency, but again, taking into account the prompt rate. Basically what we did, and then if we cannot prompt the user because we will overwhelm the user, then we will take some static policy until we collect enough data so we can start automating. But yeah, I agree. The problem with a per user model is that, we have to really be careful how we collect data for each single user.
Cool, thank you.
Okay, let's thank the speaker again.